Okay, so let's suppose you're trying to minimize polynomial expression in n variables subject to some polynomial inequalities. Now, if the degree of all the polynomials is 1, then this is just linear programming, and you can solve it like exactly in polynomial time, let's say using the ellipsoid algorithm. On the other hand, if the degree of the polynomials is at least 2, then it's very easy to encode some NP-hard problems, so you cannot hope to solve it exactly in polynomial time. So for example, in the max cut problem, you have n variables for the vertices of the graphs. Here you have two constraints. Xi squared is at most and at least 1, so xi squared equals 1. So that is enforcing that each xi is either plus or minus 1. So it's enforcing that the variables are Boolean. And then of course, minimizing or maximizing some polynomial expressions over variables that are forced to be Boolean can encode things like max cut. You'll have a degree 2 constraint, or a degree 2 optimization function. Or once you have polynomial inequalities, you can add in more fun things like max bisection. If you're representing your bits by plus or minus 1, then the bisection constraint just means that the numbers add up to 0. That's the degree 1 constraint. Or you can code, let's say, minimum vertex cover. It's written in a funny way here because I used plus or minus 1 notation for the bits. But anyway, you have degree 2 constraint for each edge, and you're trying to minimize the number of vertices in the vertex cover, and so forth. So optimizing a polynomial with polynomial constraints is certainly NP-hard. We can't hope to do it in polynomial time. But we have approximation algorithms, so we could hope to approximately come up with the optimization solution in polynomial time. So a popular strategy for that is with linear programming relaxations or semi-definite programming relaxations for these combinatorial optimization problems. And like a very hot one right now is the sum of squares hierarchy of semi-definite programming relaxations, which I wrote as exactly. That's why the slides are red. It's a family of semi-definite programming relaxations parameterized by something called D. And this D is called the degree parameter or the rounds parameter. And for every choice of a natural number D, you get like a semi-definite programming relaxation for your polynomial optimization problem. And it's really cool because it's very powerful. And this parameter D is also pretty cool because you can set it to whatever you want. And as D increases, so does the tightness of your relaxation, the quality of the relaxation, but also the runtime. So you can get potentially a trade-off between running time and quality. Okay, and if you haven't seen this stuff before, I don't have time to fully define SOS. But as an example, if you do this strategy for the max cut problem and set D to be 2, then you get the well-known Gomans-Williamson semi-definite programming relaxation for max cut, which has the property that it approximates the maximum cut to some factor 0.878 in polynomial time. Great, so this is the SOS hierarchy of SDPs. So I put some quotations up here. Don't read them too carefully, but I'll read a couple of them to you. These are from papers that I had saved to my hard drive when I was making the slides on the plane. So the first one says, the SOS hierarchy can be solved in time n to the order d for degree parameter d. And the second one says, the SOS algorithm with parameter L takes n to the order L time to run. The third one says, if in the degree d SOS proof exists, it can be found in time n to the order d. Hey, actually, I wrote that one. I was involved in this one also, and maybe this one also. Right. There's some stuff about approximation down here too, but I'll get to that. Right, so with all these quotations, you'd probably be forgiven for thinking that the SOS D relaxation can be computed in time n to the order d by semi-definite programming. However, this statement is false. Well, I cannot categorically say it's false without implying that P does not equal P space, but what I mean by that is it's not known to be true. And probably if I had to bet, I would bet on it being false rather than betting on being true. So now you might say, you know about semi-definite programming, you might say, well, usually there's this caveat that you don't solve it exactly, you solve it approximately to some exponential accuracy. So you could put this here, but that's still false. And if you're really into SOS, you might know about this thing where it's usually nicer if your polynomial optimization problem has this property called Archimedean or explicitly bounded, which basically just means that you have the constraint that all the variables that you're optimizing over are not unconstrained, but they're, let's say, bounded between plus or minus 1, which is usually a very harmless constraint. And this usually makes things nicer, but the statement's still false, even if you put this in there. Right. So let me give you an example. Since I won't fully define SOS, I'll just kind of illustrate with an example. Here's an explicit polynomial of degree 4 over 3 variables. You should think really of n variables in degree 4, but I only had room for 3. And let's just imagine the optimization problem that's completely unconstrained. Let's just minimize this on R3. Well, to make our lives simpler, instead of optimization, we can just switch to the decision version of the problem, try to decide for any particular target value, like 0, is it the case that p of xyz is greater than or equal to 0 on the reals? So this is like an example of kind of a hard problem. And so the SOS relaxation for this particular problem would be the following. The SOS relaxation is this polynomial a sum of squared polynomials? Okay, that's a relaxation, of course, because on one hand, if it is a sum of squared polynomials, that means that the polynomial is certainly non-negative on all of our 3. But the converse is not necessarily true. There's some non-negative polynomials that you cannot exactly write as a sum of squared polynomials. But remember, we're just trying to come up with some approximation algorithm. So this is the relaxation that SOS would have you do. And the reason why you move to this relaxation is like hopefully you can solve this one or decide this question in polynomial time. So why might that be the case? Well, the good thing about asking instead of it's non-negative if it's the sum of squared polynomials is that this is literally exactly 100% equivalent to asking if a certain semi-definite program is feasible. So you also don't have to look at this too carefully. But the question of whether this polynomial is a sum of squares of polynomials is exactly equal to the question of whether this semi-definite program, which has, I guess, 9 variables arranged in a matrix, where they're constrained that this matrix is supposed to be PSD, and also that these linear inequalities in the entries, linear equalities in the entries should hold. This SDP feasibility problem is the same as asking if this is a sum of squared polynomials, P. Great. So then you may say, all right, in general, an n-variable SOSD relaxation is equivalent to the feasibility problem for an SDP with about n to the d variables. And then you may say, great, so semi-definite programming is solvable in polynomial time by the ellipsoid method, let's say Grotschall-Lovász-Schreiber. And therefore, you can do SOSD in time n to the order d. Well, maybe. So no, not really. And the trouble with this little proof sketch is that this line is not true. So for example, it's a fact that whether or not you can solve the SDP feasibility problem in polynomial time is unknown. Whether you can solve it in NP is also unknown. The question of determining whether a given polynomial with rational coefficients is a sum of squares is a special case of SDP feasibility. It's also unknown if this is in NP. SDP feasibility is in p-space. That's known. It's not obvious, though, at all. Great. So what's the problem, actually? I mean, you might think, naively, why shouldn't SDP feasibility be in NP at least, right? I mean, the verifier gives you the feasible point, if it exists. Well, I mean, if you studied semi-definite programming a bit before, you kind of remember that there are some issues with this, right? For example, there exist semi-definite programs that are feasible, but the only feasible points are irrational. So of course, it's quite hard to write that down. And you might say, well, I'm just trying to approximate max cut to 0.878. I don't mind if I approximate an irrational number by a rational number to exponential precision. That's one issue. But another issue that could also be a problem is perhaps your semi-definite program is feasible, but the only feasible solutions, maybe they're rational, require exponentially many bits to write down. And that can also happen, and it's a problem. It seems like it's a problem. So let me try to give you a picture about, to remind you sort of why it can be a problem. So let's consider this a semi-definite programming feasibility problem with this little example M. So one of the constraints is that these variables form a matrix, which is PSD, the feasible region of which is some PSD cone. And then you also have these linear equalities, which are some hyperplane. And the intersection of these two objects is the feasible region. So maybe it's this yellow thing. So how does the ellipsoid algorithm attempt to decide if this feasible region is empty or not? Well, the first thing it does is it starts with a big ellipsoid, or ball in fact, of radius capital R, which just for some reason you know that if the feasible region exists, it's supposed to be inside this ball of radius capital R. And capital R should have polynomially many bits. And honestly, in the SDP case, there's no particular reason why this R should exist. So if you don't know anything else, you just maybe have to hope that R exists. And then the ellipsoid algorithm checks if the center is in the feasible region, and if it's not, it gets a separating hyperplane, and it finds a smaller ellipsoid that contains the region if it exists, and it keeps going for a while. And it keeps going for a while until it has an ellipsoid whose volume is the same as that of a ball of radius little r, which is like inverse exponential, or a rational number with polynomially many bits. And if after that point it doesn't find a point in the feasible region, then it just says, well, I guess the feasible region is so small that perhaps it's empty. So it stops there. So you can see, there's some issues with getting this to work correctly. In particular, you can think of the little r issue and the big R issue. So the little r issue is the fact that it only stops and guesses that it's not feasible if the ellipsoid gets very small. In some sense, this is always a problem in theory because, like in SDPs, right, your feasible region is the intersection of this PSD cone with like some linear equalities. So it has dimension that's not even full dimension. It'll have volume 0. So it's not going to contain a little ball if it exists of radius little r. Now, so then you kind of have to start doing some tricks, like you can inflate it artificially to try and find maybe an approximately satisfiable solution. And that can be okay. You might think approximation is okay, but you have to be a little bit careful because it's not necessarily always the case in your problem that if you approximately satisfy the polynomial constraints, even to really good accuracy, that you're in good shape. The capital R issue is very unclear to me. So I mean, if you have a semi-definite program feasibility problem, it may not be the case. And there's often no real reason why you can know that the feasible region, if it exists, is inside some exponentially big ball. And you might be a little confused because I'm going to always assume that your polynomial optimization problem includes these constraints that bounds the variables. But there's two different kinds of variables here. There's the variables, the xi in your polynomial optimization problem, but that's not the same as the variables in the semi-definite program. The variables in the semi-definite program are the coefficients of the polynomials whose sums of squares you're looking for. And it's not really obvious in most cases why those polynomials should be of small size. Right, so in the paper, I won't go over this, but I just wanted to put it on the slide. In the paper, I give some explicit example where you have a degree 2 polynomial optimization problem, quite simple degree 2 constraints, a degree 1 objective function, and it includes all the constraints. There's 2 n variables here, but they're all bounded between -1 and 1. And this optimization problem has the property that the SOS degree 2 relaxation is mathematically exact. It's not a relaxation. It gets the correct answer if you write it down. But there's a computational issue. Any sort of sum of squares certificate for the correct value of this optimization problem that's accurate to within an absolute constant 0.01 requires exponentially many bits to write down. And it's not hard. The proof is just an exercise. OK, so some conclusions. So I mentioned all these papers. Yeah, so if your motivation is just you have some degree 6 polynomial and 10 variables and you're trying to estimate its minimum, then you can feel free to go ahead and use sum of squares. But some people's motivation is to try to really show that maybe you can approximate max cut to factor 0.879 in polynomial time on the Turing machine model. And if you want to do that, then I just want to remark that you should take a little bit of care. Let me add some more conclusions. First of all, I love sum of squares. I've written some papers about sum of squares. I'm going to continue to write some papers about sum of squares. All this stuff is great in my opinion. But in fact, in many cases, specific cases, it's not too hard to ensure that everything is OK. In other words, prove that you can really get your sum of squares approximation in polynomial time or n to the order d time. But I don't actually know a general theory for when it's OK. If you just write a generic SOS relaxation of a combinatorial optimization problem, I don't know an easy way to check that indeed you can solve it approximately with the ellipsoid algorithm. Here's one case that's definitely OK, though. I mean, I didn't prove it. This is kind of known. But if your constraints are exactly that, your variables are Boolean. So you're minimizing or maximizing a polynomial expression over the hypercube, and there are no other constraints, then it's OK. You can indeed, with some tricks, solve this to accuracy, exponential accuracy, and n to the order d time. So in particular, Gomez-Williamson is OK. That's fine. And I'll just conclude with what I think is a pretty nice open problem, which is it OK when your constraint set is a superset of this? Which I think is a very common but not fully general case. In other words, if you have some SOS program of degree d, where all the variables are constrained to be Boolean, but maybe you additionally have some side constraints, additional constraints like a balancedness constraint or a vertex cover type constraints, is it possible to solve it in n to the order d time to exponential accuracy? Thank you. Yeah.
Are the requisite bounds sort of implied by rounding algorithms, though?
Not that I know of. So I mean, this issue, the issue is very similar to like the issue that arises like if you construct if you're trying to construct STP integrality caps. It's like you know this. It's like common phenomenon that you get like an STP instance that almost satisfies all the constraints. And then you have to do some like weird massaging to like try to get to literally exactly satisfy the constraints. Like that massaging is like sort of exactly analogous to what you need to do often to show that this little r problem is not a real problem. That like if you solve your STP approximately, then you can solve it exactly.
Any more questions? Is Avon in the room? Is the next speaker in the room?
Yep.
Go for it. Yes, any more questions?
So I guess all the negative results about SOS are now more impressive, right?
Yeah, I can that's fine. Yeah.
The question should have been, does the rounding algorithm imply that you can artificially relax the program and then round it with the same rounding algorithm to get the same guarantee? That should be my question.
I don't know. I mean, it depends. Like, for example, I mean, maybe a rounding algorithm relies on the triangle inequality, and then you have to ask yourself, is it sufficient for the triangle inequality to hold approximately? Well, I guess we'll have to talk about it in a second. Yeah.
Are there any reductions to other problems that where precision becomes an issue? The one I'm thinking of is like the linear combinations of square roots, and for that comes up in the Euclidean TSP.
I don't know.
That's an STP feasibility question,
Yeah, so
Yeah.
that's a special case.
but not necessarily a sum of squares feasibility. I don't know.
I see. But maybe that's another
You
example.
get such, in that problem, you get such counterexamples also, humongous precision counterexamples.
Yeah.
So there is a connection.
That's not known, Christos.
I see, sorry. You get the counterexamples, but you don't know the, yes, you don't get the family, yes, right. You get, true. Okay,
Take it away.
thanks.